little union break.
All right. So if I pick this row, well, this row might be nice because there's no negatives already in there. All right, just be nice to ourselves. But the idea is you kind of take a 3 by 3 and make it into 3 2 by 2s because 2 by 2s are easy. And it sort of makes sense on some level. There's a lot of math processes like that. When you hit a quadratic, you make it into 2 first degree things. You kind of break it down into smaller parts. So this would be 4, and actually it would be, what's the little cofactor matrix? Plus, negative, plus, negative. Negative 4 times the determinant of the stuff that's not in the thing you picked. The number or the whole thing. So it would be, so this, they can't be in this, so it would be negative 1, 2, negative 1, 3. Now this is the first time you're seeing this. I might have to bring a little handout for my other classes. I always forget when I approach this that maybe some of you guys haven't done this in a while, or maybe never.
The IJKs, you do the back.
Okay.
So the 401.
Now that's not done, right?
Imagine we have a vector like this.
So, but you guys get the idea. So the thing that's in the background is this guy.
Do one, yeah. And you subtract your J.
That kind of tells you what the coefficient's sign is going to be.
So the next one would be 0.
Yeah. So the next one would officially be 0. But just to kind of write it, what would the little 2 by 2 be?
1, 2.
1, 2, 6, 3. And then it would be minus 1 times the determinant of 1, negative 1, 6, negative 1. So again, just like a bunch of math is, learn a process for this, get a higher level thing, and build it off the process you know already.
How do you pick the 2 by 2s that are?
Oh, so I picked this row. Is that cool?
Yeah.
And then I said 4 times everything that's not in 4's row or column. So that's this. It's kind of beautiful. And then you just go through, and you can't forget this poor little dude, right? Or you're screwed. So then this would be negative 3 plus 2, negative 1, negative 4 is 4. Did I do that right? What's the same we did? Plus 0, yay! And then negative 1 plus 6, 5, minus 5, you get negative 1. Hopefully, something like that. What's more important is, do you know the process of setting that thing up? So, with that in mind,
So an nth order determinant follows a pattern, an alternating pattern like you have there. So with the 2-term determinant, that's why the first A and B were positive and B and C were negative.
beautiful. I love it. Are you talking about what this looks like for this
Yeah.
kind of thing? Yeah, beautiful. I love it.
The middle term is always negative.
And of course, this leads into how to write the inverse of this, which we're not going to go to. So coming back, what was the functions I just had up here? X squared and 2x squared minus x, right?
Yeah.
So the Wronskian for this is the specific determinant. It's the determinant of the original functions, the first derivatives, the second derivatives, as many derivatives as you have functions, right? So obviously, if you have a function that's not, well, I'm not going to go there. Let's see. This one, they have functions that are eventually going to go to 0. That's not a problem. So now the second row would be all their derivatives. Cool.
1, 2.
Yeah, so 1, 2x,
Then 4.
and then derivatives.
0, 2, 4.
So obviously, well, not so obvious to be honest. Almost no matter what you do, you're going to involve stuff. So, but what row or column would you guys like to expand around?
0, 2.
Sure, you can do that, or this one, you know. So you get positive 0 times, who cares, negative 2 times, right? Is that cool? So if I use 2, it's going to be everything not in there, so it's going to be, let me just go ahead and write it.
4x minus.
And then it's going to be plus 4 times this little chunk here. The corners are always nice. So then you get, now what did we say? We said, or we noticed, we proved that these are linearly dependent, right? So let's see what we get at the end. I can't, well, I've got to figure out how to show you some idea why this works the way it does. But,
Where'd you get the negative 2?
2 is here, which has a negative coefficient. Yeah. This is a little cofactor matrix, if I remember. It's been a while since I taught that. Let's see, what do we got here? Okay, negative 2 times 4x squared minus x minus 2x squared plus x. Is that cool? And then you get, just kind of rushing through the way, 2x squared minus x squared. So you get negative 8x squared. The x's go away inside, so screw them. You could have done that too, Jeff, but oh well, too bad for you. You get plus 8x squared. And there again, Jeff, oh well, this is just the kind of day it is. All cancel to get 0.
Yeah.
So in general, if you, now you got to be careful. If you get 0, you can't say that they're linearly independent, right? If it's not 0 ever, then they are plain old independent. You could get an answer, obviously you could get an answer that's dependent on x. And then there are places where it is 0 and you have to exclude those places. That won't be in your interval of solution.
Wait, can you say that again?
Sure. So if the answer here would have been x, is that always not 0? It's 0 at x. Really amazing. So I'd have to exclude 0 from my interval of solution, whatever it's going to end up being. Yes?
So for it to be linear independent.
The Wronskian cannot come out to be 0.
Okay.
If it is 0 at certain values of x, that's salvageable, right? But if it comes out to be 0, you ain't saving it. Now, to be honest, there are some funky combinations of functions that's why I said it a little bit carefully. If it's 0, you can't say that they're linearly independent, because there are funky little combination functions that come out to be 0 that actually are independent. But let's not worry. There's always counterexamples and stuff. Okay, is that how far I wanted to get? Blah, 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 blah. And then I have an example about that. I already did the general solution for homogeneous equations. I already talked about that. It's just collecting all those specific solutions you got with C's. That's going to become just kind of, like I intimated, it's going to become the first step of any DE solution, higher order DE solution. And then it gets into non-homogeneous equations, which I might as well leave for next time. I want to warn you, you should always be doing this. And this is the hardest thing to do as a human, especially as a student with little time. You need to read ahead. 4.2, you want to read ahead a bit. Even if it doesn't make much sense, you want to have something to come in to ground what I'm going to talk about on. 4.2 is not that rough. It's a beautiful idea. In fact, well, shit, somebody should have stopped me because now I'm going to have to show you the idea.
Oh,
No, nothing major. Let's say, and you're like, your definition. If I have a DE order 2, and I know I have y1, I have a function, I know that works. There has to be another one, right? Because it's order 2. So, and what's got to be, now here's the thing I forget to say. To make a complete, what's called the fundamental set of solutions, you have to have, in this case, if it was a homogeneous DE order 2, it would have to have 2 parts to it. They would have to be linearly independent, which only makes sense, right? If I said one solution is x and the other one is 2x, and you'd be like, you're stupid. You're going to put a c in front of it, so that captures the other dude. You didn't really find a second solution. So if I know one solution, the second one has to be, it has to be linearly independent. I like it differently. But different in a much more specific way. It can't be 2x and 3x. So in fact, now watch, I want you to really get this. If that has to be linearly independent, that means that y2 cannot just be a constant times y1, right? Which means that y2 has to be a function times y1. Which leads to a substitution method. That is a substitution. So 4.2 is called reduction of order. If you think about it, if I know an answer, I should be able to use it to reduce the order of my DE because I already know an answer. If I use it, I should be able to reduce the order because how many more answers are there? 1. So the order should kind of reduce to match the fact that I only have one more solution to find. It's a beautiful naming of this thing. And it's a relatively simple process, but it's, you know, that's all I can say about it, you know? Yes?
So this only works for order 2?
No. You can extend it. Oh my God! And to be honest, this actually has ties to the Ronskin, and this is kind of like where I could discuss a proof of why the Ronskin does what it does. But I'm not going to go there. We're going to deal with just second order to begin with. But if I knew 2 solutions to a third order, I could use both of them to get the third solution in the same way. It just does get ugly in the process.
Yeah.
Yes. Cool. All right.
Have a good night. Have a
You
good
too.
weekend.
Did I?
Oh, it's Wednesday.
Yes, it is.
Did that.
Nice to meet
Oh, that's right. I want to give you this here.
Chapter 4, summer picture. Video.
Dude, you could borrow a book.
We bought the book today.
Okay. So you
I
can.
had an unexpected expenditure last month, so I had to wait.
I hate this. This is a long one. So
I blew a switch on at the house.
there's section 4.1.
I wanted to ask you about the test.
Thank you.
Yeah. So you need to make it up. Is that right? Okay. So as soon as you get a makeup made, yeah, it's been a crazy time. I don't like to have a lot of time transpire between when it happened and when you're going to take it. So hopefully I get that done soon. I'll email you back when it's ready, and then you call and make an appointment. I'll tell you in the email.
Just wondering what your opinion was on like finding outside sources,
Because
like looking. 'Cause